this term, isn't it? So after today's 3-week break for Easter. I thought we'd finish by looking at the special cases of Dirichlet's theorem. And these are an application of things that we know, things that we've built up about quadratic residues as well. So remember, Dirichlet's theorem, normally stated as Dirichlet's theorem on primes in arithmetic progressions or primes in arithmetic sequences. It says that the arithmetic sequence a plus nb, where n goes 0 to infinity, so this is the sequence a plus b, a plus 2b, etc. Continues like that. So it's an arithmetic sequence. It's got some initial term a, and then it just goes up in fixed step size b. And it says that this contains an infinite amount of primes, an infinite number of primes, if and only if GCD of A and B is equal to 1. Okay. Clearly, maybe there's an edge case. Yeah, let's say B not equal to 0. We're actually talking about a proper sequence of numbers. If B wasn't 0, they'd all. If B was 0, they'd all just be A. So that's not particularly interesting. So as long as B isn't 0, see clearly if this greatest common divisor was greater than 1, so if A and B had a greatest common divisor of 3, say, then 3 would be, each element of the sequence would be divisible by that 3. Okay? So maybe if A was 3, it would contain 1 prime at the start, but then everything after it would be composite. But if the GCD of A and B is equal to 1, then these numbers aren't obviously composite, all of them. They will certainly mostly be composite numbers, but Dirichlet's theorem says that there will always be an infinite number of primes in there. And that is one way of, this is one way of showing that the primes are kind of randomly distributed through the sequence of numbers. Okay? The primes, in the way they're distributed through the integers, they don't show preference for any particular congruence class of anything with respect to anything, apart from avoiding, obviously, composite congruence classes. Because all these numbers, if you consider all these numbers modulo b, they're all congruent to A modulo b. So this infinite sequence of numbers is an infinite sequence. In fact, it's all the positive numbers that are in the congruence class of A modulo b. And Dirichlet's theorem is saying, well, as long as this congruence class isn't obviously what you'd call a composite congruence class, where every number is divisible by some number, which it would be if the GCD of AB is 1. If that isn't the case, then that congruence class will contain an infinite number of primes. So this is kind of saying the primes, they don't avoid any congruence classes, modulo anything, apart from avoiding, by definition, the obviously composite congruence classes. So this is one way of illustrating this. This is one piece of evidence that tells us intuitively or vaguely that the primes are randomly distributed through the sequence of integers without any very simple pattern. Okay? Now, proving this needs a lot of theory, which we haven't had the time to develop. What we can access, though, are some special cases of it. Okay? Now, I've already proved one for you, didn't I? We already proved the case of the sequence 4n minus 1. So where A is minus 1 and the B was 4. We already proved that. So this requires This requires more theory in general, but special cases are available to us. So last time we saw the set of all numbers 4n minus 1. So this sequence, 4n minus 1, this contains an infinite number of primes. Okay, we proved that last time. The proofs are modeled, remember, on Euclid's proof that there's an infinite number of primes in all the integers. Remember the way that proof went? It's proof by contradiction. Assume there's only a finite number. Derive from that assumption an obvious contradiction in terms of one of the prime factors of a certain number, and then from that you conclude then that there has to be an infinite number of primes. Well, these special cases which we're proving are all kind of based on that. So for now, for next we're going to see now we'll consider the sequence 8k plus 3. K equals 0 to infinity. I've just written it with a k because that's the way it is in the question. Just the second last question on page 70. Prove there's an infinite number of primes in this sequence. So this is the congruence class of 3 modulo 8. Okay, it's not a composite congruence class. It's not, all the numbers in it aren't obviously composites because 3 and 8 are coprime. Okay, there's certainly plenty of composite numbers. Most of the numbers in there are composite. But Dirichlet's theorem asserts that there's an infinite number of primes in this. And we can prove this in this special case. Now, the kind of large number to use in the proof modeled on Euclid's proof that there's an infinite number of primes, the kind of number to use is given to us here. Okay? You see the pattern there. We're going to use this. We're going to assume there's only a finite number of primes in there, multiply them all together, square them, and add 2. So that's the hint. So it's something about the properties of this number. When you add all the finite number of primes of this form together, square it and add 2, there's something self-contradictory about that number, which we're going to discover. Okay? So we'll assume there are only a finite number of primes here. There are certainly some, okay, because 3 is of this form, 11 is of this form, 14 is some prime, but 17 is of this, no, 11, sorry, I'm adding 8 each time. 3 is of this form, 11 is of this form, 19 is of this form, 27 isn't, 35 isn't, but 43 is. So there's quite a few primes in the beginning of the sequence, so there's certainly some of them. So we'll assume that there's only a finite number of them. Let's call them P1 up to PS. And then we'll consider the number this large number n, which is given by, well, here's what we're going to do. We're going to multiply them all together, square it, and add 2. This is certainly an integer. Plus 2. So what we do is, so this is a large integer. So this large integer n has prime factors. So we'll consider a prime factor q of capital N. So q divides n. Well, that implies that q divides this square plus 2. P1 up to PS. Well, that implies that minus 2 is congruent to this square modulo q. In other words, minus 2 is a quadratic residue modulo q. Okay. So by definition, so we assume there's only a finite number of primes. By construction, we construct this special number n such that any prime factor that n has, and we know it must have some, any prime factor that it has, minus 2 is a quadratic residue modulo that prime factor. Now, what can we do from here? Can we break this Legendre symbol down any? Well, yeah, we can factorize it. And it factorizes as the Legendre symbol minus 1q times the Legendre symbol 2q. Now we've studied these Legendre symbols. We proved after we arrived at Euler's criterion for evaluating a general Legendre symbol nq, we examined the special cases of n equals minus 1 and n equals 2. We got nice results about them based on the congruence class. This one was based on the congruence class of q mod 4. This one was based on the congruence class of q mod 8. So we can make use of those now. But what have we got? We've got the product of these two equal to plus 1. Well, if the product is plus 1, that tells you they both have the same sign. So they're either both plus 1 or they're both minus 1. Yeah, that's the only way when you multiply the two Legendre symbols that you can get plus 1. So they either have to be both positive or both negative. So you either have minus 1q is equal to 2q is equal to minus 1, or minus 1q equals 2q equals plus 1. So what were those results about minus 1 and 2? These are back on page 59.
So Q, why does it
Excuse me.
Why does it mean one of the factors is minus 1?
Sorry?
Why does it mean one of the factors is minus 1?
I'm saying they're either both minus 1 or they're both plus 1.
Oh, right.
Because when you multiply them together, you get plus 1.
Yeah.
Individually, both are either plus or minus 1. I'm saying they can't be opposites. If they're opposites, then the product would be minus 1. So now we're making use of the. So we know one of these conditions must be true. Well, if they're both minus 1, this would mean that. So in this minus 1 case, we would have q was congruent to 3 mod 4, and q would be congruent to plus or minus 3 mod 8. And in the plus 1 case, q would be congruent to 1 mod 4, and q would be congruent to plus or minus 1 mod 8.
So how do you? Oh, you just
So I'm reading off from theorems from the two results on page 59. Theorem 8.5 and theorem 8.6.
Where? Aren't you just trying to get the modulus? Aren't you trying to get q to equal -1?
Q to equal -1?
Yeah, in that situation, 3 mod 4.
Well, you see, well, I can look now at these two statements about Q and I can reconcile them into just one statement, which we'll do now, because this +1 in quotes, sorry, the -1 in quotes is referring to this top line. See, how can something be 3 mod 4? Well, and then it can either be 3 mod 8 or -3. Now, another way of saying -3 mod 8 is 5. This is 3 or 5 mod 8, and that's 1 or 7 mod 8 on that line. Well, you see, Q can't be congruent to 5 mod 8. If Q was congruent to 5 mod 8, it would be congruent to 1 modulo 4. So if you've got something which is congruent to 5 mod 8, because 4 is a factor of 8, the congruence class of Q modulo 4 would just be determined by the congruence class of this residue mod 4, and that is congruent to 1 mod 4. So that means this -3 can't happen in combination with this +3 here. So it has to be that Q is congruent to 3 mod 8. And in the +1 case, the Q can't be congruent to 7 modulo 8, because in that case, it would have to be congruent to 3 mod 4, because 7 is congruent to 3 mod 4. So it must be that it's congruent to 1 mod 8. Now here's our 3 mod 8. What we're trying to say see, Q is a prime divisor of n. We've got down here now that Q is either 1 mod 8 or 3 mod 8. So we've shown that a prime Q dividing Q divides n, that implies Q is congruent to 1 or 3 modulo 8. Now, what do we know about n? So we're trying to prove that there's an infinite number of primes congruent to 3 mod 8 here. That's what we're trying to do in this case. So what is n modulo 8? Well, if you look back at how n was defined, how did we construct n? We constructed n by taking a bunch of primes which are all congruent to 3 modulo 8, multiplying them together, squaring them, and then adding 2. Now, this square you can take inside the brackets. You can think of n as being p1 squared times p2 squared times p3 squared, and so on. Now, each of the pi's are congruent to 3 mod 8. So when you square each of them, you get 1 mod 8. And when you multiply together a lot of things which are congruent to 1 mod 8, you get something congruent to 1 mod 8. So congruence classes are multiply them together like that. So n seems to be something congruent to 1 mod 8 plus 2. So n is very definitely congruent to 3 mod 8. N is congruent to 3 mod 8, since n is equal to p1 squared, p2 squared, ps squared plus 2. And each pi is congruent to 3 mod 8. So when you square it, it's 3 squared is 9, but that's 1 modulo 8. So it's a load of 1s. Modulo 8, n is a load of 1s multiplied together plus 2. So it's 3 mod 8. So n is congruent to 3 mod 8. So that tells us that it must have at least one prime which is congruent to 3 mod 8. Okay? It can't be the case that all of n's prime factors are congruent to 1 modulo 8. Because n is the product of all its prime factors, and if they're all congruent to 1 mod 8, then n itself will be congruent to 1 mod 8. But it ain't. N is congruent to 3 mod 8. And if n is congruent to 3 mod 8, it must have at least one prime factor q congruent to 3 mod 8. Because if they were, I mean, we've known through we know through the quadratic residues any prime factor of n is 1 or 3 mod 8, but they can't all be 1. Then n would be 1 mod 8. So it must have at least one prime factor q congruent to 3 mod 8. Let q be such a prime factor. And here we get our contradiction. Because remember, we've assumed that there's only a finite number of these. And we've captured them all in the P1 to PS. So if Q is a prime factor 3 mod 8, it must be one of those P's. But if it also simultaneously divides n, that implies that this Q will divide n minus the square of the product of all of those. In other words, that Q divides 2. But that is clearly now a contradiction. Okay? Q is supposed to be a prime number dividing 2. There's only one prime number that divides 2. 2. But simultaneously, it's also supposed to be congruent to 3 mod 8. And what is 2 congruent to mod 8?
2.
What is 2 congruent to modulo 8? 2. Bit of a trick question. There's too many 2s in it. 2 is, what's the congruence class of 2 modulo 8? Well, it's the congruence class of 2. Which is certainly different to the congruence class of 3. So this statement here, Q dividing 2, and this statement here, Q congruent to 3 mod 8, are clearly in contradiction to one another. Because this one is trying to say Q equals 2. How can you have 2 being congruent to 3 modulo 8? 2 is not congruent to 3 modulo 8. They're different congruence classes. To be congruent to each other, your difference has to be divisible by 8. But the difference between 2 and 3 is 1. And 1 ain't divisible by 8. So with these kind of things, when you constantly need to be stepping back, kind of literally zooming out of the argument. What was the argument in brief from top to bottom? We started off, we said, assume there's only a finite number of primes in the congruence class of 3, modulo 8. We named them. This shows you the power of actually, naming everything that's floating around. If I'm assuming there's only a finite number of them, let's name them. P1, P2, P3, all the way up to some last one, Ps. And there's a finite number, so there is a last one. You gather them together, multiply them together, square it, add 2. This squaring and adding on 2, this brings in the notion of the quadratic residue status of 2. So you form this number n. N must have prime factors. Any prime factor q that it has, minus 2 is going to be a quadratic residue modulo 2. And using previous results, kind of work it and work it and work it and work it. Using previous results on quadratic residues, if q divides n, q has to be 1 or 3 modulo 8.
Where do you form where did you form n? Like something squared plus 2? I mean,
formed n up here. So the n was given to us in the question. I mean, discovering this proof would be kind of discovering the correct formula for n and exploiting the quadratic residues in this way.
No, I mean, like, why was it specifically this squared, specifically plus 2?
It's constructed in such a way to lead to a contradiction when we assume there's only a finite number of these primes. So it's a little bit mysterious about why we formed n like this as opposed to any other way.
What? So that's just always the rule? N is going to be?
No, it's not always the rule. It's the thing that works in this specific case of the congruence class of 3 modulo 8.
So how did you know that this number?
Well, it's a standard result. It's a standard known result, an easy case of Dirichlet's theorem.
So it's the rule then? But
Sorry?
It's the rule to apply this time.
It is the rule for the congruence class of 3 modulo 8. You form the n like this, and you'll be able to get the contradiction out of it.
Yeah.
So the prime factors of q have to be 1 or 3 mod 8. But you see, n itself is 3 mod 8. So these prime factors, they can't all be 1. If they were all 1, n would be forced to be 1 mod 8 as well, because n is the product of its primes, prime factors. And there must be at least one prime factor congruent to 3 mod 8. And there you go. If it is congruent to 3 mod 8, it must be one of the PIs by assumption. But if it is one of the PIs and it also divides n, therefore it divides the difference, which is 2. But come on, if you're dividing 2 and your prime number, you have to be 2. But then you can't be congruent to 3 mod 8. So that's the contradiction. So what led to that contradiction? It was that first word here, assume. We're not allowed to make this assumption. We know there are prime factors in this sequence. There's a few at the beginning of the sequence. We're not allowed to assume there's a finite number. Therefore, there must be an infinite. A classic structure of proof by contradiction. The assumption leads to a contradiction, therefore the assumption can't hold. So therefore, 8k plus 3 from n equals 1 to infinity has an infinite number of primes. And it's intriguing that we can prove that at all. Just using the theory that we've developed, culminating in the quadratic residues, of course, it does get you this special case of Dirichlet's theorem. Now there's another one given in part C. You can do a similar thing. And if you really want to investigate, I should have looked this up, but I imagine there are some other accessible cases of Dirichlet's theorem. So if you really wanted to set out on a good, explore yourselves, you could consider simple congruence classes. So small enough moduli. Consider some of the congruence classes and see if you can, from what we know about quadratic residues and so on, see if you can tease out another proof of a special case of Dirichlet's theorem. So here's another one, part C on page 70. So here we're dealing with the sequence 6k plus 1, k equals 0 to infinity. And, well, okay, we know from authority, we know from Dirichlet's theorem, there's an infinite number of primes here. Can we prove it using what we know about quadratic residues and so on? Well, we set it up in the structure of the thing is the same. So we assume there's a finite number. P1, P2, up to PS. And there's certainly some primes, because 7 is in here, 13 is in here, 19 is in here. They're all prime at the beginning. But then you go 19, well, 25 isn't prime. 31 is prime again. 37 is prime. 43 is prime. They're mostly prime at the beginning. But trust me, the primes will fade out, of course. Primes become scarcer further you go down into the sequence of integers. So they do peter out, but there should be an infinite number of them. So we make this false assumption. Well, it'll turn out to be false. It's going to lead to a contradiction. We consider this number n. Okay, this time we throw a 2 in there, so that's going to have some significance. We square them all and we add 3 this time. So any prime divisor q well, if it divides n, q divides n means q divides this, and that means minus 3 is a quadratic residue. Because minus 3 is going to be congruent to this thing, and this thing is obviously a square. It's the square of all that. It's obviously a square. So any prime q dividing n satisfies minus 3 mod q. That Legendre symbol is plus 1. So we do the same thing. We factorize it. Okay, this is plus 1. So this implies that both of them are either plus 1 or minus 1. Okay, because their product is plus 1. Okay. If the product was minus 1, they'd have to one be plus, the other be minus, or vice versa. But here they're either about plus and right about minus. And we do have results. We know completely when minus 1 is a quadratic residue modulo q, based on q mod 4. And we know completely when 3 is a quadratic residue modulo q. That's based on q mod 12. And for that, we need a quadratic reciprocity. We derive the result about q mod 3 using the quadratic reciprocity law. So this one is relying on the full weight of kind of machinery that he built up in the course. So what are the congruent statements here? Well, if minus 1 is plus 1 modulo q, then q has to be 1 modulo 4. And if 3q is plus 1, then q has to be plus or minus 1 modulo 12. So we'll write that as 1 or 11 modulo 12. That's example 8.4 for the status of 3, theorem 8.5 for the status of minus 1. So that's the case, or in the negative 1 case, q has to be 3 modulo 4, or q has to be plus or minus 5, so I'll write that as 5 or 7 modulo 12. So one of these two lines must be true about q. But the residue status of something of q modulo 4 is only compatible with one of these congruence classes modulo 12. So that simplifies it down. If something is 1 mod 4, it has to be 1 mod 12. It can't be 11 mod 12, because 11 is congruent to 3 modulo 4, because it's 8 plus 3. So you examine these two statements about q on this line. You see, it has to be that q is congruent to 1 modulo 12. Or you examine these two down here. you'll see it has to be that Q, so which is the one here? Here it has to be 7 modulo 12. 7 mod 12 is certainly congruent to 3 mod 4. 5 mod 12 is congruent to 1 mod 4. So that's incompatible with Q being congruent to 3. So the second line, it has to be Q is congruent to 7 modulo 12. So in summary, Q divides N implies Q is congruent to 1 or 7 modulo 12. Well, what's this saying about? Now we're dealing with we're dealing with congruence classes modulo 6. Now both of these are congruent to 1 mod 6. If something is 1 mod 12 or 7 mod 12, then both of those congruence classes are contained within the congruence class of 1 modulo 6. So if it's 1 mod 6, 1 mod 6, this implies that Q is equal to one of the PIs. Well, you get the story. If it's equal to one of the PIs, then it very definitely divides 3. Okay, because if Q is one of these PIs here, it divides this square thing here. It also divides N, then it also must divide 3, because 3 is N minus this square. They're both divisible by Q, then Q divides 3. But there is only one prime which divides 3, and that is 3 itself. But now that's a clear contradiction, because you cannot be 3 and simultaneously be congruent to 1 modulo 6, okay? Because 3 is not congruent to 1 modulo 6. So our assumption is false. So 6k plus 1, this sequence, k equals 0 to infinity, has an infinite number of primes. Now, I slipped something past you there, so I had a little flight there a second ago. So I glanced back up at the n. What did I notice about the n? I noticed that we threw in a 2 there in the n. So we defined our n as 2p1 ps whole squared plus 3. And I didn't use in the argument anything. I didn't rely on this 2 being there anywhere in the argument, so why the hell is it there? Well, I slipped something past you. Well, to even start talking about Legendre symbol, something mod q. No, it's in the use of 3q. This result that we established about the Legendre symbol 3 mod q, that made use of the quadratic reciprocity law. The quadratic reciprocity law only refers to odd primes. Meaning, when you say odd primes, you're excluding the first prime too from the discussion. So, talking about the residue status of 3 modulo q, and using this result that 3 mod q is determined by q's mod 12, that relies on the fact that Q is odd, that it's not this one special even prime, namely 2. So here, we use the fact that Q is not the prime 2. But 2 is a prime, so there's no I mean, why can't 2 divide n? We see if we'd left off the 2 there, then 2 would divide n, because the p's, all being congruent to 1 mod 6, are all odd numbers. And you're squaring them, you still have an odd number. Then you add on an odd number 3, you get an even number. So there'd be one or more factors of 2 inside n. But we want to make this kind of talk here about quadratic reciprocity law. So we don't want Q to be 2. So one way to ensure that Q is not 2 is to pop the prime 2 in here, because then that makes n odd. You got an even number inside the bracket, because it's got divisible by 2. You're squaring it, so it's still even. You're adding 3, it's odd. So by construction, the prime factor Q of n cannot be equal to 2, because n is constructed in such a way as to make it odd. So notice, n is constructed to be odd. So any prime factor Q is not 2. So we can talk about the quadratic reciprocity law involving 2 and 3. So we can make use of that result about the residue status of 3 modulo Q and relating that to Q modulo 12. That's a good place to finish off, seeing these nice 2 special cases of Dirichlet's theorem. If you look in the kind of book we've kind of been following the treatment of is the Introductory to Analytic Number Theory by Tom Apostle. And in there, it does have a full treatment of the proof of Dirichlet's theorem. So if you're interested in checking out what the further number theory looks like, what the general approach to Dirichlet's theorem is, you can look to Tom Apostle's book or another equivalent book to see what some of the details are like. But it's a good place there to leave it for the moment. So after Easter, we'll do a lot of revision work, looking at some past exam questions.